So here's my code for solving this problem of the heat equation for the glass window that's warm on one side, cold on the other side. And actually, I've got it all in one cell here, which maybe wasn't the smartest thing. But so I'll just walk through this code and we'll see how it solves the problem. Upstairs here are kind of the various parameters of the problem that we need. So they relate to the glass, and then they relate to the discrete space-time that we're going to work in. So just for concreteness, I've made the glass, let's see, 0.5 centimeter thick, 5 millimeters thick. And I looked up the diffusivity for glass, and it's this, actually it's not this value here, I was playing around with it, it's 10 times smaller than this value. It's this value here, about 0.34. If this was steel, it would be, like 100 times bigger or something like that, because, steel conducts thermally, conducts heat a lot, and the glass is relatively insulating because one's an insulator and one's a conductor. Anyway, so these are two parameters that we need for our problem. You see the units here, meters squared per second. You can think of those units in terms of, well, look, that is a constant between a space, first order partial differential with respect to space, and second order partial differential with respect to time. So it has to have those units. Downstairs here, I'm just specifying, remember that A and that H for the space grid and the time grid. So I've made my spatial grid so that there's 100 steps from one side of the window to the other side of the window. And I've made my time grid so that one step in time is 0.1 of a millisecond. So that's defined those lines of code define my space-time grid, basically. Okay, the other parameters I needed to introduce were related to the boundary conditions and the initial conditions. So that's these guys here. So there are both initial and boundary conditions here. We've got the boundary conditions are 24 degrees inside the house and 0 degrees outside the house. And so I called those T low and T high. And then the initial condition is that initial temperature of the glass. And I said, somehow I magically prepared it at 10 degrees Celsius. And so that's both boundary and initial conditions. I'm going to work with two arrays, kind of like we work with two arrays for Laplace's equation. When we did the solution of Laplace's equation, we had an array phi and an array phi prime. They were two-dimensional arrays because we were solving this function of x and y. Actually, in this case, I'm going to work with a one-dimensional array, t and t prime. So the one-dimensional array t for temperature is just the one-dimensional array of space points. And so I'm going to set that initially to the initial temperature of 10 degrees or for all the points from one side of the glass to the other side of the glass. And then I'm going to use this leapfrog method to calculate the temperature profile of the next time interval by that difference equation. And I'll make that t prime. And then I'll just iterate and iterate and iterate on that. So I'll just step through time, calculating from t prime, and then I'll reset t to be t prime and calculate again. So and reiterate and iterate. So really the key thing here is that I'm declaring the array t to have, correspond to my spatial lattice. And I also declare the array T prime to correspond to my spatial lattice. And then for the initial temperature, the starting temperature, I've got to set up the initial conditions. So I've actually set here one end to be hot, one end to be cold, and everywhere else to be that 10 degrees Celsius. Okay. So now I'm going to shoot down here. Down here is the difference equation. Let me just mention a couple of other things. This bit of code here, I'm going to make plots of the temperature profile, the temperature gradient at different times. And I'm just going to make these plots at these 5 times. So why are you doing that? So that's all T1, T2, T3, T4, T5 are. Just 5 different times from 10 milliseconds, a very short time, to 10 seconds. This is just a helper. This epsilon is just to help me recognize when I'm close to one of those times and I want to make the plot. So that's all that. You'll see how that works. This is just a clock. I want to record when I take each of the steps where I am in time, because I want to plot at certain times. So this is just a clock for me. And then if you think back to that difference equation, there is a coefficient in that difference equation. It includes the diffusivity, obviously depends on the material, and it includes how the size of your steps in space and time. And it was this guy here. So it was the diffusivity times the time step divided by the square of the space steps. One's linear and one's quadratic because of its first or second order differential equations. So this is just convenient to redefine as one parameter. Okay. So all the work, all the solution is done here. I mean, it's very, very straightforward to solve this heat equation in this problem in terms of the actual calculation. It's just done it in a for loop. And in this for loop, we're going to step through the space points, say from one end of the rod to the other end of the rod. And we're going to calculate for each space point the new temperature, so T prime, based on the prior temperature, T. And to do that, all we have to do is add this piece from the difference equation. So it contains that constant we talked about. And then it contains the this kind of earlier temperature, T, at the location of T prime, and the temperatures on either side of that, on the left and right of that. And remember, if there was no heat flow, we wouldn't need these pieces here, the temperatures on either side. Okay, so that all the work is done in this little step here. The while loop is just to get me, keep me going through this, so these time steps, until I reach what I've declared to be the end time, which is basically when I plot the last time spectrum. And there must be a better way of doing this, but this is how I made these plots at different times. I said if I reached a time, one of those times, T1, T2, T3, T4, T5, within that epsilon, that little interval, then I would make the plot. And I would plot the temperature gradient. Okay, so let's run this. This might take 30 seconds or a minute, I don't know.
So we're running the loop in the middle part of the grid, right? Not on the end.
We're running, yeah, so we don't want to change the temperatures right on the end. Yeah, yeah. So you look, that's a very good point. So the array, we've skipped the first and we skipped the last element by this range here. Oh, we're done. Okay, so this is the result of our calculation. I'm plotting, if you look at these, I'm plotting just the temperature as a function of the position. Remember, we divided the width of the glass, the thickness of the glass, into 100 steps here. So this is from the warm side of the glass on the left to the hot, the warm side on the left to the cold side on the right. The warm side, the air was at 24 degrees Celsius. So that's 24 degrees Celsius up here. The cold side, it was at 0 degrees Celsius. And we made, as you pointed out, that very first layer of the glass on the warm side, we fixed it to be 24. And that very last layer on the cold side of glass, we fixed it to be 0. So every one of these lines that corresponds to the temperature gradient at different times after we've let this heat equation go has 24 degrees Celsius here and 0 degrees Celsius here. So at 0.01 seconds, so 10 milliseconds, we've got this gradient in blue. So if you look at that gradient in blue, most of the glass is still at 10 degrees Celsius. The only regions of the glass where the temperature is changing is the far right and the far left. So heat has flowed into the glass from the warm side and warmed it up a bit. And heat has flowed out on the cold side and cooled it down a bit. So you see, it's right near the edge here, it's a little bit warmer. Right near the edge here, it's a little bit cooler than it started out. And then just like that steel rod that we dropped into the bath of water, if we look at later and later times, so I'm looking at a 10 times later, this must be a mistake. What was it? 0.5, yeah. I'm not going to run it all again though, because it'd take ages. So a tenth of a second, half a second, 1 second, you really see how heat is flowing in and more of the warm side of the glass is warming up. Heat is flowing out, more and more of the cold side of the glass is cooling down. And then finally, if we wait a long time, so this is waiting 10 seconds, we get to that expectation where we've kind of reached an equilibrium, or at least, no, we reached a steady state, I should say, where heat is just continuously flowing through the glass. So every little slice of the glass, there's the same amount of heat flowing through it. So it's in steady state, like current flowing in a circuit in steady state. And there's a uniform temperature decrease from the warm side of the glass to the cold side of the glass. And so all that came out of this little difference equation here.